Hello, welcome back. This is part 2 of chapter 19 on the Milky Way galaxy. In this video, we will look at galactic recycling. Our goals for learning: how is gas recycled in our galaxy? Where do stars tend to form in our galaxy? This is a picture of the star-gas-star cycle. We've talked about this concept before. If you follow around the cycle, we can start it anywhere we want because it's a cycle, but let's start right here about where we were in chapter 16 when we looked at the birth of stars. So here we have molecular clouds that lead to star formation. So the beginning of stars, the birth of stars, is what we talked about in chapter 16. And then those stars go through their lives. They have nuclear fusion. We talked about that in chapter 14 when we learned about the sun, and also in the life of stars in chapter 17. And then as the stars come to their end of their lives, they return gas to outer space. And that could be in the form of a planetary nebula. It could be in the form of a hot bubble, such as this one shown here. But it's taking those heavier elements that were produced and putting it out into space. And whereas in this picture, it's a hot bubble, millions of Kelvin giving off X-rays, it will eventually cool down and get dimmer, and atoms will start to form. The electrons will join with the nuclei and become atoms. So here we have atomic clouds, and in the picture here, it says atomic hydrogen clouds. And those clouds are mostly hydrogen, but there are other elements as well. And then eventually they cool down more so that the atoms can join together to make molecules. And then they are molecular clouds. And from these molecular clouds, new stars can form, and the cycle repeats. So the star-gas-star cycle, the galaxy recycles gas from old stars into new star systems. A lower mass star, I want you to remember, returns its gas to interstellar space through stellar winds and planetary nebulae. And there you have a planetary nebula with the white dwarf in the middle, that leftover core. X-rays from hot gas in supernova remnants reveal newly made heavy elements. And the very heaviest elements, particularly the elements heavier than iron, which is element number 26, are all formed in that sudden supernova where there's enough energy to fuse heavy elements. A supernova remnant cools and begins to emit visible light as it expands. New elements made by a supernova mix into the interstellar medium. Radio emission in supernova remnants is from particles accelerated to near light speed. Many cosmic rays probably come from supernovae. So let's talk about these cosmic rays. Cosmic rays are the energetic particles. They are traveling throughout space. They come from supernovae, and they are dangerous in large amounts, large energies, to human bodies, to biological tissue. Fortunately, we have an atmosphere. We have 60 miles of air that blocks us from many cosmic rays. However, we do still get some radiation from space. It's what we call in the medical field background radiation. There's some radiation you just can't hide from and shield yourself from, and it's just radiation that we are all exposed to. However, the higher you go up in the atmosphere, the less shielding you have from the atmosphere, and the more exposure you have to radiation. And so medical physicists, health physicists are interested in how much radiation exposure people get on airplane flights. Now, taking a few flights throughout your life, even throughout the year, is not going to be dangerous, but this is of particular concern to people who are on airplane flights for a living, airline crews and pilots, etc. This is a listing of, for one particular day, this is April 27th, 2020, of somebody got dose ratings from different flights to see of charter flights versus commercial flights, and which ones got the highest dose from outer space, from cosmic rays, and which ones got the least. And so, for example, let's look at these. The top 5 commercial flights, Southwest Airlines, American Airlines. Again, this is just these particular flights on these particular days. This column, notice the second column says the dose rate times at sea level. So if you're down at sea level, and we're near sea level in Porterville, but you get the most shielding from the atmosphere, but you do get some cosmic radiation. So this is saying that on these flights, people got 60 times the dose that they would have gotten if they were down at sea level. It's at an altitude of 41,000 feet. That's on the high end of where commercial flights go. Often they're in the high 30,000s, like 37, 38,000. And it makes sense that the higher altitude and the longer distance, that's going to get the most radiation. So these flights are such as from LA to Chicago, Chicago to Atlanta, and the duration of the flight. And then we can see even the bottom 5 commercial flights. These were at lower altitude, so 27, 28, 30,000, with still 25, 26, 27 times the dose rate that one would get at sea level. And they were shorter duration flights, so Oakland to Santa Ana, Minneapolis to Chicago, LA to San Jose, so shorter distances. This shows radiation levels at different altitudes over about a 6-year period. And here we have a smaller aircraft flying at 25,000 feet, a commercial aircraft, typically 40,000, and a weather balloon in the stratosphere. Commercial aircraft don't go this high. But you can see the radiation doses, and the vertical axis here says dose rate times sea level. So typically the smaller aircraft going at 25,000 feet is getting, you can see this looks between 10 and 15, maybe as high as 20 times the sea level dose rate. Higher altitude means higher dose rate, and way high in the stratosphere, 67,000 feet, can get as much as 90 times the sea level dose rate. So the lesson is the higher up in elevation you are, the more exposure you have to cosmic rays. Let's go back out into the galaxy. As the gas that was formed inside stars, it gets put out into the galaxy, and first it's very hot. If it's from a supernova, it's from an X-ray bubble that is millions of Kelvin. It eventually cools down. And so it can become an atomic cloud, an atomic gas cloud. Often they're called atomic hydrogen gas clouds because they are mostly hydrogen. But as I said before, they will have other elements in them as well. So atomic hydrogen gas forms as the hot gas cools, allowing electrons to join with protons. So remember, that's what an atom is. You have the nuclei and then the electrons in orbit around it. Now, as time goes on, this gas cloud will continue to cool, and it gets cool enough so that it allows atoms to combine into molecules. And then we have molecular clouds. This shows some molecular clouds in the constellation Orion. You see the Orion constellation, and in Orion's sword, we have various molecular clouds, and these are stellar nurseries. This is a region where stars are actively being formed. The composition of these clouds is mostly molecular hydrogen. Notice it doesn't just say H, it says H2, so that's a molecule of hydrogen. And then about 28% helium. Helium doesn't form into molecules, it's just atoms of helium. It's a small percentage, about 1% of carbon monoxide, and many other molecules as well. And this is where stars are formed. Gravity forms stars out of the gas and molecular clouds, completing the star-gas-star cycle. Here's our summary of galactic recycling. Stars make new elements by fusion. You learned about that in chapter 17. The dying stars expel gas and new elements, producing hot bubbles that are about 1,000,000 Kelvin, so that's going to give off X-rays. The hot gas cools, allowing atomic hydrogen clouds to form. That's going to be anywhere between the very low temperature of 100 up to about 10,000 Kelvin. Now remember, the surface of the sun is 5,800 Kelvin, so some of these gas clouds are actually higher temperature than the surface of the sun. But eventually they cool down. Further cooling permits molecules to form, making molecular clouds. And typically these molecular clouds are about as cold as space gets, 30 Kelvin. And then gravity can form new stars. And with those stars, planets, comets, asteroids, all those other things that we find in a star system from the molecular clouds. Thought question: where will the galaxy's gas be in 1 trillion years? Now I put 1 trillion years thinking about that's a long time compared to the life of stars. The galaxy, we estimate, has only been around for about 13 billion years. And so you think about the life of stars. Stars like our sun live for about 10 billion years. Now 1 trillion years is 100 times that, meaning a time for many, many generations of stars like our sun to come and go, form new stars, die, form a new generation of stars. So many, many generations of stars. So where will the galaxy's gas be in 1 trillion years? We expect it'll be locked into white dwarfs and low mass stars. As the gas keeps going through several generations of stars, there is less and less gas to make new stars, and eventually there should be nothing, no interstellar medium, or very little of it, and basically just a whole lot of white dwarfs and low mass stars. We observe the star-gas star cycle operating the Milky Way's disk using many different wavelengths of light. Here we see a comparison. The picture down below is looking at the Milky Way, that stream of milk, as the ancient Greeks thought it was, going across the sky. On the bottom, we're looking at it with visible light. And you can see some brightness and a lot of dark. Now, the dark is actually not the absence of stars, but rather it is dust that's in the disk, and it's blocking out the light that's coming from a lot of those stars and the center. But let's look at the top. Radio waves. So radio telescopes can see particularly atomic hydrogen. Particularly the wavelength is 21 centimeter radio waves emitted by atomic hydrogen show where gas has cooled and settled into the disk. Now we can see a comparison between visible light on the bottom and another wavelength of radio. Radio waves from carbon monoxide show the locations of molecular clouds. So we can use this particular wavelength that is given off by, it's the emission lines of carbon monoxide, and we can map out where all the carbon monoxide is in the galaxy. This up top is long wavelength infrared. Long wavelength infrared emission shows where young stars are heating dust grains. So it's a way of mapping out the dust in the galaxy. Infrared light reveals stars whose visible light is blocked by gas clouds. This is short wavelength infrared, which means it's pretty close to visible light. And you can see just by changing the wavelength a bit, all the light from the bright center of the galaxy that we can't see here on Earth. We can't see it because we're looking through 27,000 light years of dust. And all that dust is blocking the light from the center of the galaxy. But if we could see in infrared, and we have telescopes that can do that, then all that infrared light would come through the dust and we'd be able to see a bright center to the galaxy. Fortunately, we have infrared telescopes that can see it for us. Moving on to higher frequencies, X-rays are observed from hot gas above and below the Milky Way's disk. Even higher frequencies, gamma rays, show where cosmic rays from supernovae collide with atomic nuclei in gas clouds. So the gamma rays are from the collisions between the cosmic rays and atomic nuclei. It's a way of mapping out the atomic nuclei. It's another way of mapping out where the gas clouds are. Let's now look at where stars form in the galaxy. In this picture from Hubble Space Telescope of the Orion Nebula, it's an ionization nebula, also known as an emission nebula. And this is where stars form, one of many regions where stars form. Emission nebulae, also known as ionization nebulae, are found around short-lived high-mass stars, signifying active star formation. Remember on the Hertzsprung-Russell diagram, the short-lived high-mass stars, those are the blue ones up and to the left. If we have these nebulae, that means that there is a lot of star formation going on, so a lot of stars that go through more quickly this star-gas-star cycle. This is a chart of various emission nebulae that we find particularly in that Orion Nebula. And you can see such things as atomic helium, ionized oxygen, doubly ionized oxygen, so the ionization shows that it's going to be higher energy, higher temperature. Reflection nebulae scatter the light from stars. Why do reflection nebulae look bluer than the nearby stars? For the same reason that our sky is blue. So I want you to remember, when you see a reflection nebula, it is blue because there is starlight from a nearby star, and that starlight has all the colors of the rainbow. And when that starlight hits the molecules, the dust in the reflection nebula, it'll scatter blue in all directions, so it looks blue. Again, that's the same reason our sky is blue. That's what our atmosphere does to the sunlight. Above and below the disk, remember, is the halo of the galaxy. We see no ionization nebulae. We see no blue stars, so there is no star formation going on in the halo. There tend to be very old clusters of stars. But in the disk, we do see ionization nebulae. We do see blue stars. We see a lot of active star formation. Much of the star formation in the disk happens in the spiral arms. This is a picture of the Whirlpool galaxy. It's actually two companion galaxies, but let's focus on the larger one that's towards the left. You can see those spiral arms. That's where most star formation happens. You notice as you look at the picture, the various colors. You see yellow, particularly in the bulge, but you see red, you see blue. Wherever you see blue, that just shows that the light is dominated by bluish stars. There's a lot of those bright blue stars, which means there's a lot of active star formation. The spiral arms are waves of star formation. What happens with a spiral arm, the gas clouds get squeezed as they move into the spiral arms. The squeezing of the clouds triggers star formation, and young stars flow out of the spiral arms. In this video, what have we learned? How is gas recycled in our galaxy? Gas from dying stars mixes new elements into the interstellar medium, which slowly cools, making the molecular clouds where stars form. Those stars will eventually return much of their matter to interstellar space. And where do stars tend to form in our galaxy? Active star-forming regions contain molecular clouds, hot stars, and ionization nebulae. Much of the star formation in our galaxy happens in the spiral arms. And that is it for part 2 on galactic recycling in the Milky Way. Have a great day.